Okay, the additional module of Physics GCSE all begins with the idea of motion. That is, how do things move? Now, we're going to need to start with a little bit of maths. This is a graph, something you're all very, very familiar with. It has two axes, a y-axis and an x-axis, and they allow us to compare two different variables and see how those variables change over time. If I draw a straight line on this graph, you should be able to calculate the gradient of that line. Gradient just tells us how steep the line is. Well, how we do that is we pick 2 points on the line and we'll draw a triangle. And we'll see how much does y change, and we'll call that delta, or change in y. So how much has this variable changed? We can do exactly the same with the x-coordinate, and we can say, well, how much has the x-coordinate changed? What's delta x, the change in that x-coordinate? And we can then calculate the gradient. And the gradient of any straight line graph will always be the change in y divided by the change in x. Now, with that in mind, we can start to do a little bit of physics. Because with a little bit of physics, we can start to see how things move and how we can express motion in terms of graphs. This is going to be a distance time graph, or a displacement time graph. So we can't slow down time. We're always going to be moving along this x-axis. The question is, does your displacement change? If I'm 1 meter away from a bench, then I have a displacement of 1 meter. And if I stay 1 meter away, time doesn't stop, but my displacement doesn't change. If my displacement is changing, that's motion. So let's draw an imaginary journey. Let's have something going at a constant speed. That gives me a straight line. And if it's a high constant speed, that would be a very, very steep line, a large gradient. If I then take a break, I have one of those horizontal lines where my displacement stays exactly the same regardless of how long you stay there. And then let's move off again at a slightly slower speed. So here I have a distance or displacement time graph with 3 different sections. How do we work out gradient? Well, in this case, the gradient is just going to be, well, the change in y-coordinate, which is how much my distance has changed, divided by my change in x-coordinate, which is how much time it's taken. And distance divided by time, you should recognize straight away as being the formula for speed. Or, for this topic, we're going to talk about that being the formula for velocity. Velocity, key word for this module. Velocity is just speed in a certain direction. Speed tells you how fast something is going. Velocity tells you how fast it's going and in precisely which direction. With velocity in mind, we can show how the velocity of an object changes with respect to time. So this would be a velocity time graph. Now, for this entire first section of our distance time graph, it's a straight line, it has a constant gradient, and the gradient of this graph is velocity. It has a constant velocity, so we can show that as a horizontal line on a velocity time graph. In this section, it also has a constant velocity, but a velocity of 0. There is no change in distance or displacement. So I can represent that section of the graph with a horizontal line along the x-axis, 0 velocity. This third section of the graph, I've started to move a little bit faster, but nowhere near as fast as I was at the start. So I have a third section of the graph, a constant speed, but a lower constant speed than at the start of the journey. Obviously, this would be a very dull graph if that's all I ever showed. Velocity time graphs can show changes in speed or accelerations. So I can draw a straight line here, a constant acceleration. And then if I want, I can even draw a line with a negative gradient, a deceleration, something slowing down. How can we use this graph to find things out? Well, same again, what's my change in velocity? What's my change in y-coordinate? Well, I can say that's my end speed minus my start speed, and if I divide that by the change in time, you get an equation that you should recognize as being a formula for acceleration. Acceleration, change in speed, divided by the time it takes. There is one more thing that you can do with a velocity time graph, and that's have a look at the area under the graph. If you have a look at that area, you will see that it is a speed multiplied by a time, speed times time, is the distance travelled. The area under a velocity time graph is the distance travelled on that journey. Now that's nice and easy for this bit of the graph where we're going at a constant speed, but it even works for areas where you're changing speed. Now thankfully in this GCSE syllabus, you're only expected to deal with constant accelerations, which means you can easily divide up the area under a graph into a rectangle, a trapezium, a triangle, things that you know how to calculate the area of from maths. So really straightforward, velocity time graphs, distance time graphs, you can use the gradients to work out velocity and acceleration, and you can use the area under this velocity time graph to calculate the distance travelled. Now in this case, we've just seen we've got something slowing down, a deceleration, and there's one specific application of deceleration that they do like you to know about in this syllabus, and that's the idea of stopping distance. How far does a car travel in the time it takes it to stop? And that's the easiest equation in the entire syllabus, because all it is thinking distance. Now that is the time it takes for your brain to process that something is in front of you that requires you to stop the car. It's a mental processing time. It's how far you travel whilst you recognise that a rabbit has hopped in front of your car or another car is coming the other way. It's the thinking distance, the time between the light entering your eyeball and your foot slamming onto the brake. And that will be affected by all kinds of things. How bright the light is, how good your eyesight is, how awake you are, how distracted you are, how drunk you are. All of those things would have an effect. All you do is add that thinking distance to the braking distance. Now the braking distance is just reliant on the physical properties of the car and the road. How heavy is the car? How fast is the car travelling? How good is the grip on its tyres? How efficient are its brakes? Is the road surface wet or icy? All of those things will affect the braking distance, but together they add up to give you the stopping distance. We've just mentioned brakes, and brakes use a force to slow the car down. And you'll see that motion is always dependent on forces. Isaac Newton famously wrote 3 laws which describe all motion. Just about. They do at GCSE anyway. His 3 laws. Newton's first law basically says forces change velocity. This idea that velocity will not change without a force. Now if you look back to what we did a moment ago, we said that velocity is speed in a certain direction. So any change in speed or direction counts as a change in velocity. So forces cause things to change speed or change velocity. Newton's second law tells you how much that change happens. And he wrote this as an equation, F equals m times a. The size of the force is equal to the mass times the acceleration. So you can see how much something accelerates by knowing how much mass there is and what size the force is causing it to change velocity. Newton's third law says that 2 things interacting will exert equal and opposite forces on each other. So if I kick a football, the football actually exerts the same force on me as I do on it. Now imagine for a moment, thinking especially about those first 2 laws, forces changing velocities, and the size of the force giving you that size of acceleration. Let's imagine a car for a moment. Marvel at my high quality artwork. Here's a car. It has 2 forces acting on it. It has an engine force pushing forwards. And that engine force, you can see from the size of the arrow, is quite significant. But there will always be another force trying to slow it down. The force that always tries to stop things from moving we call friction, and it can take a few different forms. It could be the friction of 2 solid surfaces rubbing together, like when you sandpaper some wood or rub your hands together. But similarly, you could have a fluid resistance there, a drag force, the force of air resistance as you try to move through air, or water resistance if you were, for some strange reason, driving through water. But you can see straight away from Newton's laws that if these forces are balanced, if the friction is the same as the engine force in the opposite direction, then overall there is no resultant force. 2 balanced forces will stay at exactly the same speed in exactly the same direction. 2 unbalanced forces If one of these forces was bigger than the other, then you would see a change in velocity, an acceleration. Now in this case, if the engine force is significantly bigger, you will see a car accelerating forwards, getting faster. But if for some reason the frictional force was bigger than the engine force, if you put the brake on instead of the accelerator, so there was no engine force, just frictional forces pulling backwards, this car would also be accelerating, slowing down, decelerating if you like. One final example, let's imagine for a moment that we have a parachuter who's going to jump out of a plane. And again, high quality artwork. There is his parachute vaguely attached to his backpack. Now this parachuter will have a force pulling him down. Now it's worth pointing out at this point that that force pulling him down is his weight, because weight is a force measured in newtons. And weight, remember, is the mass in kilograms multiplied by the gravitational field strength in newtons per kilogram. So this weight, this force pulling him down, that is a constant. It always stays the same because he stays with the same mass. It doesn't become any more or less parachuter. But there will also be a frictional force trying to slow him down. And the faster he goes, the bigger that frictional force will be. The faster he goes, the more he will feel the air pushing against him. So let's draw a velocity time graph of this parachuter. As he jumps out of the plane, his weight is the only force that really matters. There's very, very little friction because he's hardly moving. So he starts to accelerate, very unbalanced forces. So he starts to speed up. Now, as he gets a little bit faster, this frictional force starts to increase. Now, weight still wins, so he's still speeding up, but there is less of a bias towards weight. So there is a lower resultant force, a lower acceleration, and that gradually decreases and decreases and decreases until when friction absolutely balances weight, there is no resultant force. And he's reached what we call a terminal velocity, a velocity where he cannot go any faster. Now, unfortunately, at this terminal velocity, he would die. So what does he do? He opens his parachute, and at this point, he opens his chute. Now, when he's opened his chute, suddenly he's made friction so much bigger because the air has got a whole parachute to push against, not just a puny man. And that means that there will be a big deceleration because now this force is much, much bigger. But as he slows down, the frictional force gets less and less. So the acceleration gets less and less until, once more, the friction and the weight are balanced and he's reached another terminal velocity. Now, hopefully, if he's wearing a well-designed parachute and he's pulled it in time, he reaches that terminal velocity slow enough to survive before he hits the ground.